Well, today Willow is officially back to work. She just came off of medical leave. Today she's working in the Twisted Willow studio with my wife. She's going to have a bunch of ladies in here, and she's going to be in charge of them today. But she's also kind of giving me instructions on everything I got to do next door too. My wife's business room and my business room are right next to each other, and so she gave me specific instructions on what I had to get done today, and I'm going to go try to accomplish that right now. And then she's going to stay in here and watch over the ladies. This is her office. Willow's in her office right now, and she kind of watches over things that happen here at the table. So you're going to make sure that they stay straight over here. Can you kind of make them keep a noise down over here? They don't get too laughing and too loud. Because sometimes that messes up my psyche over there, and it messes up my thinking. All right. Thank you, Willow. I appreciate all your hard work. Glad to have you back to work. Yeah, we'll maybe have a party later. All right. All right. Thank you. Thank you guys for watching. Hello and welcome to Timeout Tuesday for Radio Hound Tube Radio Restoration's YouTube channel. This is John from Indiana, and I'm glad you came back for another visit. Today we're going to go back over just a little bit. We had some viewer responses, and I wanted to try to address some of those things they're talking about. I'm going to talk a little bit about more about the this is on the question we had, was referencing the output transformers and how we would select the right output transformer, and it's basically specifically referencing the load resistance and the fixed bias and the cathode bias, and I'm going to try to describe that a little bit. And also I'm going to show you how to ohm out a speaker too, because that question was asked also too, and then I might add something new on also. So we'll get right into it. I hope you stay with us today, and I hope you enjoy the video today. Thank you. Well, good morning. I want to start off this Timeout Tuesday by making a little correction real quick. I kind of mentioned it in one of the other videos, but I'm just going to make sure, or I can't remember if I mentioned in the intro, but when I was making the correction to the last Timeout Tuesday, I was making the correction where I got the right number here because a viewer had pointed out that I'd clipped on the wrong pin, so I made that correction. But while I was talking about it, I overheard myself talking about measuring this side and then measuring this side, and I called this the first IF, and I called this other side the second IF, and that's not true. This is the first IF, and over here is the second IF. This is the primary, and this is the secondary. So I should have said the primary, the first IF, and the secondary, the first IF. And nobody pointed it out to me, but I just caught the fact that I did that, and I thought that might confuse somebody thinking this is one IF and this is another. No, this is all the same first IF. It was just a slip of the tongue there. This is the first IF primary, first IF secondary, second IF primary, second IF secondary. That's cleared up. Okay. Now I had a viewer reach out to me, and we're going to go ahead and deal with this next. Reached out to me on two things. I'm going to deal with the first one first. I hope that I do this justice, and if I don't, some of you that are more knowledgeable, please pipe in and correct me. But he asked about when I was referencing on replacing the output transformer, when I was referencing the book, the fixed bias and the cathode bias. I'm gonna bring this other book in here so you can see what I'm talking about. When we were looking at the total load resistance right here, and if you can see at the top here, it says, let me pull it down in the picture a little bit better. It says fixed bias and cathode bias. And on our radio, all the numbers were the same. It's 7,000 ohms across there. Now that was for a single tube. If you go on down here to the the push-pull tube like we got is 10,000, but it's still, no matter whether it's fixed bias or cathode bias, it's still 10,000. But sometimes that can be different. And there's, matter of fact, there's a lot of times that'll be different, and you have a different value depending on whether it's fixed bias or cathode bias. And so he asked me, what does these two terms mean, fixed bias and cathode bias? Well, in the video that I just aired, let's see, on Friday, the part 14, I think, of the schematic series. I do reference that a little bit, but I'm going to go just in a little bit deeper depth on the Timeout Tuesday today, and just maybe, hopefully I can explain it a little bit better so you can understand. All right, if you have something that's fixed bias, just keep this in mind, that it's going to be dealing with the grid here. This is your power tubes right here. These are your push-pull power tubes. And there's a grid wire that comes in here to that push-pull power tube. There's one on this one right here, and then you can see the one coming in on this. Remember, it'll come in from the left side on the schematic, and it'll come into your tube, and this will be on your control grid, okay? So that's where your audio is going to come into that tube, all right? But it has to be biased. Now, how these tubes work, and I'm going to go back over this one more time. I'll go back over a bunch of times, but this time I'm going to go back over it. This is your heater right here, and basically you're heating that up. It's almost like a filament in a light bulb, and you're going to heat that up. And remember, I said this is like the frying pan. This is your cathode, this little curved thing. And the cathode, the frying pan, the little fire underneath just looks like, pretend that's a little flame, and that's heating up this cathode. Well, this cathode is negative charge, and it's got a lot of electrons on there, and those electrons are just dying to get off of there and won't go somewhere. Well, while you're heating that up, the electrons are wanting to move off of this here. Well, what we did is, remember, we sent the high voltage from down here coming out of the rectifiers, and that high voltage is going up in to this plate. This is your anode. That's your cathode. This is your anode. And we put high voltage here. Well, electrons like that high voltage. They like that positive voltage, and they want to try to come over. So if you didn't have these two wires right here in the way, they would just pile on. They would just come uncontrollably up here because you're heating this up, and electrons boil off, and they want to come right to here. All right, well, they put these grids in the way because that's how you can control this tube. You can either turn it on or shut it off. Depending on how much positive or how much negative you add to this, you can make this tube like go out of control, or we go cold. Let's call it too hot, too cold. All right. Well, if something's fixed bias, that means you're doing something right here on this grid, okay? And what you're doing is you're giving a constant negative charge to this grid. All right, what that does is that controls the flow of these electrons over here. Pretend that this is, maybe see how they got the little dashed line? Just pretend that's like a big piece of screen wire. And that screen wire allows some electrons through, but some of them are going to catch on that negative because it's going to kind of block some of those coming through. And depending on how much you charge this thing up or discharge this thing, make it too negative or too positive, will depend on how many electrons get to flow through here. If you didn't have this in the way, they would just flow through uncontrollably, and this tube would just go super hot and burn up. So you have to control that. So this is a bias, but it's a constant negative. Now you can have it adjustable, like a lot of the tube amp guys. They'll have adjustments on there, like a little trim pot out here, and they can trim how much of that what negative level that level that's set at. And now understand, just a small slight change over here can either burn your tube up or make it run too cold. You can do a lot of damage over here if you're not careful. So you don't want to make big changes, but these guys will do this to control that level of how much negativity is coming into this grid, and that's called a fixed bias. They have it fixed. Then there's other ones that are factory fixed, and there's no adjustment to it. It's just a set negative voltage that comes through right here. Now, how to tell if you've got a fixed bias or a cathode bias, and let me talk about cathode bias first, and then I'll tell you about how to tell the difference. All right. Now, when you have a fixed bias, like say you're going to have a constant flow in here are the exact same. It's not going to fluctuate. It's going to be the same negative. Whether you trimmed it out, you can trim it up higher, trim it up lower, but still once you trim it, it's going to be constant. All right. And then also on that same token, if you have fixed bias, your cathode is going these two cathodes, you have push-pull, it's going to be hooked together right here like this, but it's going to go straight to ground. This is going to connect to ground, kind of like, let me find one over here. I think I saw one. Yeah, right here. Here's one that the cathode goes straight to ground. This is your ground symbol. All right, so bottom line is it's going to go straight to ground. All right, so in that case, if this was fixed bias, this cathode would be going straight to ground. All right, now if it's cathode biased, then some things will happen, and good identifiers on this. Cathode bias, you'll have your grids both hooked to resistors, and if you look at this one, got a grid hooked to resistors. This grid's coming out and it's hooked to a resistor right here. These are resistors. All right, and then also on cathode bias, they'll have you'll have, when you come off of this, instead of going to ground, it's going to go to a resistor. And I'll explain, hopefully I can explain why here in a minute. All right, so when you see evidence of this, you're going to be cathode biased. Now, to kind of explain the difference, and I'm not taking any of this from my own wisdom. This is just stuff that I've learned and stuff you can get on the internet. You can go out and find it right now. But a good example I read was that when you're doing fixed bias, you're kind of adjusting the engine idle. But now the difference between fixed bias is in cathode bias, you're gonna have different sounds and tone quality, and that's why the tube amp guys will have a little potentiometer out here so they can adjust that up or down, because they can mess with the change of the sound. Because if you're playing a guitar and you got a guitar amp, you want to, sometimes they like distortion, and sometimes they like, so they'll tweak that a little bit, and they'll turn that little trim pot a little bit, and what that'll do is affect the sound over here, depending on whether it's fixed bias or cathode bias. It will give it a different sound, okay? But anyway, I'm kind of losing my train of thought there, but bottom line is you'll see this resistor at the end of that cathode before it goes to ground. See, over here is where it goes to ground, so it's going to go through this and then go to ground, okay? All right, so bottom line on this is we kind of already are learning what our tubes are, because this cathode is not going directly to ground. It's going through resistance to ground. And then on the other side, you have your grids that are connected through resistors, and they'll eventually go back to ground too, right through here. And so that kind of tells you right off the bat that you probably have a cathode bias here. The point I was going to go to about the car analogy is this is more like an engine idle, okay? Where you're adjusting, you get in there, carburetor, adjust and idle your car just the way you like it, okay? And on this side, it's more like a governor. On the cathode bias, it's more like a governor. It'll get it. Now, the difference between these two is if I was to pull these tubes and throw another set of tubes in here, if this was fixed bias, then I have to readjust this bias right here, because each tube operates a little different, and you need also good matching tubes. Like when you put this in a tube tester and this one in a tube tester, they got to be pretty close to the same number on each other. Otherwise, you're going to have them working too hard, one working too hard, not the other, because you're dealing with something that you have to control. This is something that you're controlling. If you do on this side with the cathode bias, then what that does is it automatically controls that for you. So you could swap out these tubes and it'll automatically correct that for you, because it fluctuates with the voltage that's coming through there. All right, so now I'm going to show you a little bit about kind of I guess how that works. Okay, anytime you put a resistor in the path of something, you got your voltage. Anytime you have your resistor in the path, what that does is it blocks that voltage. So what it's doing is it's actually elevating the voltage here. Most of these guys are usually at zero on the cathodes, or zero or very close to zero. and 0 volts. So what you're doing here by putting that resistor in the path to ground, what you're doing is you're elevating the voltage on this cathode. And what that does is it makes the tube think that this is negative, in which it might not be. It might be just 0 volts. But if you're going above 0 volts here, it's going to make this more negative than this one, I guess. But it's the comparison between this grid and the cathode. All right, so you got the comparison between the two, and it's always, for the tube to work right, the tube has to think that this is giving negative voltage, even if it might not be. Like if you're not using, if you're like you're grounding these out through a resistor, you might have a voltage there, but this is going to be more positive than this. So the tube don't care; it don't know the difference. It don't know if you're giving negative voltage here or positive voltage here. But bottom line is this is going to be more positive than this. This has to be more negative than that to make this tube start operating right. I don't know if I'm making any sense on that. But the bottom line is, for a lot of these old radios, you'll see a lot of cathode bias in here because it helps control this a lot better. And then you see, you get into a little later models and stuff, you'll probably start seeing some of the fixed bias, and you'll also see maybe a little trim pot involved to where you can adjust that bias to make it work right for your tubes. And I hope that helps explain it. And I mentioned when I was doing one of the schematic videos, I call it grid bias too, because there's a lot of terms for it. You got grid bias, and when you're talking about the fixed bias, the grid bias, or they call it the adjustable fixed bias, or the just plain fixed bias where you can't adjust it. There's like 2 or 3 terms for that, and then you got your cathode bias over here. But biasing a tube basically is driving this negativity of this center part of this tube to make the tube operate and within its perimeters. So you can't put too much and you can't put too little. You can't run the tube too hot or too cold. Too cold, it's not going to operate right, and it's going to sound weird. And then if you have it too hot, you're going to burn these tubes up that are very expensive tubes. So the bottom line, I hope that answered your question to the viewer that asked that. And if there's any more questions, I'm getting excited because I'm starting getting these kind of questions instead of, I love it that somebody tells me that we're doing a good job, but I want to, I love answering, I love dealing with this kind of stuff, and I'll probably deal with a lot of these on the Timeout Tuesday videos, these questions that you guys have. If it's something that I can't just answer real quick on the comments, if I can answer it real quick, I'll just answer it. But if it's something that needs a little more explanation, and we'll get more into this as like we'll look at each radio and see whether it's fixed bias or cathode bias on these output tubes, okay? Now, they use that on a lot of these other tubes too, but the most important place is right here. And I think what I'm going to try to describe here in a minute, I told you there's going to be something extra on this video, is I think I'm going to try to explain the plate dissipation. Now, you have I did the output transformers out here on the right, and whatever you do with this output transformers, you're going to change it out. You're going to be affecting this tube, and you're going to make them run too hot or too cold on this side. Well, the same thing with the fixed bias and cathode bias, you can make these run too hot or too cold on this side. So you're dealing with both sides of these output tubes are really important. And change out your output transformer. You got to make sure you do your math so you can get the right one, so these things won't run too hot or too cold. But over here, if you send the wrong bias into this, whether you send it in through the cathode or through the grid, if you send the wrong bias in, you're going to run too hot or too cold. Either way, you don't want to burn these tubes up, and if you do it the other way, you're not going to be hearing anything, or it's going to be really muffled or quiet or distorted, and you got to get the bias set right. Okay, most of the time on these old radios, the bias is already set because it's cathode bias, and it automatically will fix itself. So if you're changing out tubes here, it won't affect it as much. Just you do have to make sure all these resistors, these are critical resistors right through here and through here. This resistor looks like it's part of the candom, and really it's not. It's tacked onto the end of the candom. All right, so if that generates any more questions, bring them on. The other thing, like I say, I'm going to go into plate dissipation. That's going to be a new term you're going to learn, and I'm going to try to show you just real quick. I'm not an expert on this, but as far as how to calculate your plate dissipation over here, so you can figure out what bias you need in here. So hopefully I can help you with that. Then also the viewer asked me to show how to measure the voice coil, and I thought I'd just show a real quick little thing on that too. So I'll hold on and we'll be right back. All right, before we get into the plate dissipation part of this, I wanted to kind of show you real quick. He asked how the best way to tell what ohm voice coil you have. Well, your voice coil sits right down in the bottom right here of the speaker. It's a little wire coil, and I think I might have one laying out somewhere. I'll show you in a minute. But basically, you'll see little wires that come right here, and they'll usually have a little tap on the outside. You'll see the little silver thing on the top too. But some are designed differently, but almost all of them have this little wire. There's one on each side. There's one down in there. I got my yellow, it's on the other side, but I got my yellow one hooked to it. But you should have two wires coming into there, all right? The little wires. Now, on the outside here, you might have 3 or 4, like this one here has 4, because it's doing the humbucking coil too. But we'll get into that another time. But just to measure your voice coil, all you need to do is hook onto those 2 little wires that are coming in. Sometimes they'll be attached right to the speaker, like this one. This one goes on and attaches. That's where they attach at right here. This is your voice coil down inside here. That little on the other side of this little cardboard cone, it's wrapped around with a little coil of wire, and that's your voice coil. And then when we charge up this field coil, and we get electricity flowing through that, what that does is magnetizes that pole in the middle, this big steel pole here. It'll magnetize that, and then this voice coil sits around that. You can't tell it, but there's a little gap between, let me see if I can push this up and down, maybe you can see it. This moves up and down on that coil, and as this gets the energy through there with your audio signal coming through this, it's gonna energize that little coil that's around it, and it's gonna let that coil move up and down. I don't know if you can tell if that's moving or not, but it is. But and a lot of times, if you don't have that spaced right, like when you're replacing a cone, we put little plastic spacers. And if you ever watch anybody do this, you put a little plastic strip on this side. They usually put 4 in here, 1 on each quadrant, and that'll give the right spacing away from that, so you don't have any grinding noise when you're pushing that, when that coil's moving up and down on that. It shouldn't be touching. It just should be right close to it. But basically, that's kind of in a nutshell what we did. So as you can see, I clipped on down here. This is for the viewers to ask, and then all you do is put your multimeter on to ohms, and see I'm getting 6.4 ohms. It's not going to read 8 ohms, okay? It's not going to read 4 ohms, but it's going to read close to that. Usually it's a little bit under that. Like I've had 4 ohm speakers read all the way from 1 ohm to 3.8 ohms, you know, but never just 4 ohms. Now, if you pull that thing out, you might get a little bit more accurate, but bottom line is it's not going to read exactly. I can tell you right now, this is an 8 ohm speaker just because it's above the 4 ohms, and usually you don't. I mentioned in that video too about 6 ohms. You're not going to probably see that in these old radios here. You're not going to see a 6 ohm speaker. It's either 4 or 8 usually. And that being said, then if it's above the 4, it's going to be the 8. And I'll go into later. I do not want to mess with that right now, but I'll go into later why it's not reading exactly 8 ohms. But there's a lot of variations in there that create those differences that you have. Okay, and bottom line is, if you get that right there, you got an 8 ohm speaker. Anything in the 6 to 7s and 8s, but it's going to be an 8 ohm speaker. So I know our speaker is 8 ohms right here, this speaker. All right, I hope that answered your question on that. And This will help you to identify what speaker you have. But it's just a little, it's like a little copper wire that runs across there, and it's usually not insulated. It's just usually a little metal wire, and that goes into that speaker cone. So if you have any questions, just reach out on that. Thank you. All right, I promised you something else now, and I promised you I'd give you a little bit of information on the two items right here. We used this side on the last Timeout Tuesday video to show you how to calculate to pick the right kind of output transformer, and that would be on this side of these are output tubes, that'd be on this side of the output tubes. Now we're going to calculate what it takes on this side of the output tubes. That way you can keep these guys happy in the middle. We got the right output transformer now we got to figure out our biasing, because we have to bias these tubes properly or otherwise it'll be a problem. All right, so that's what this side of my chart is about. It helps you to figure out things. Now I want to have a disclaimer here. In voltage, a lot of times, people misunderstand this, but when you have a voltage, yes, voltage can kill you, but usually it's the current that gets you, because you can take a lot of volts, especially if you got the right equipment like I got here, but it only takes a half an amp of current to kill you. Which is not very much. It's a very unsafe thing unless you have the right safety equipment and pay attention. So you follow at your own risk on this. But I always tell you to put one hand in the pocket. Get rid of your watches and rings when you're calculating current. Whenever you flip your meter over there to the current side, you want to be careful, because even the leads can be dangerous for you. So I just ask you to be real careful when you're doing this. But you have to calculate your current. And what we're calculating today is try to calculate the plate dissipation. You want to figure out how hot. That dissipation means watts. How many watts are these things going to be pulling, these two output tubes? And we're going to calculate that with our bias setting. If our bias setting is wrong, then we can adjust it, and I'll show you how to do that. But what we first have to know is the current. And how we get that current is we have to measure, and since we decided that we were cathode biased here, this is our cathode right here on these two tubes, and they have center tap that comes out of the cathode, comes down here, and it goes to these resistors right here. Well, on that resistor, you got to measure between there and ground, okay? So you're going to clip on right here, right at the end of that 40 ohm, and then the other lead, the two leads here on your multimeter, one's going to go right here, and the other one's going to go right there, all right? And we're going to measure across that, okay? And that should, in our resistance, we're going to set that to ohms on our ohms meter. And we're going to measure that resistance. It's saying that should be about 240 ohms across there, okay? Let's just say that is exactly right, that it hadn't drifted at all, and let's just say that those are right, okay? So what we'll do first is I'm just going to put this, I don't have anywhere to write. I should have set myself up. Let's just say that was 240 ohms. All right, so what I just measured right there was this middle column. I measured the resistance across there. Then with the thing powered up, when you have your radio powered up, you keep your clips on the same spot, and you figure out how many volts is across here. You're going to have a voltage drop from here to ground. It's going to be a voltage drop, and God knows what that voltage is. I don't know, just in our hypothetical situation, but we have our ohms resistance and our voltage. Let's say our voltage drop is 70 volts, okay? All right, so we have 240 in the resistance and 70 in there. So our first column will say 70, and this one will say 240. I don't know if I can write on this or not. I'll probably take it off with alcohol. Let me try that. Okay, that'd be our 70 voltage drop. No, it's not gonna let me write on it. Let me see if I can do it with my marker. I'll probably regret this because I'll have a permanent marker on here. 70 and 240 is my resistance, okay? So now what we're doing is we're calculating the current that's going across there. And just so you know, by doing this, I'm giving your first introduction to Ohm's law. I know some have probably been introduced in school and stuff, but what we have to do now is we divide, up here it says divide J divided by K. Okay, so we're going to take this number here divided by that number. All right, so we're going to do 70 divided by 240. All right, and so that's telling me I have a 0.29 is my current. Okay, so that means it's like a little less than a 1/3 of a current. So we're going to write that in there now as 0.29. All right, and if you want to add another decimal in there, I mean, you could round that up to 29.5 or something like that, 295 or something. Bottom line is, it's about 292 actually. If you wanted to round that up, it doesn't hurt a thing, but don't really help a thing either. All right, so now what we're going to do is move over to this side now, and we have to measure the plate to cathode voltage. Okay, so we're going to be measuring, since we're measuring our output tubes and we're doing cathode bias. See, we're measuring this thing here, and we want to measure from that cathode to that plate with it running, and you'll know what your voltage is between these two. Okay, and I have no idea what that would be in real life. We're just going to put a hypothetical number in there. Okay, so let's say that's I don't know, I have no idea what it'll be. It might be a lot less, a lot more, but let's just say it's 80 volts. Okay, and then we're also going to bring this number here over into there. We want to put our plate current. Okay, so it's 0.29. Make sure you put the point in there. Okay, all right, because it's not even a 1/3 of an amp. Okay, all right, so now we got our 80 volts there and that. Now we take the O times the N. Okay, so now we're going to do our calculation over here, and we're going to do 80 volts times 0.29 equals, I don't know if I can see that, is 23.2. Okay, all right, so I can tell you right now my plate to cathode voltage is going to be a lot different, because this is saying it's going to be 23.2. Well, and I'll show you how to look this up later, but since we got 6 V6 tubes on these 6 V6 output tubes, their max that they like is for this situation is a push-pull. But here's where the calculation was wrong, and I just wanted to do it like this to make you think for a minute. Okay, this calculation for that, for the calculation for the current through here. Okay, when we did that calculation, one thing that we have to take into consideration is this right here is 2 tubes. 2 tubes are sharing this current. Okay, so what we have to do is we have to take this current right here divided by 2. If you went with the 0.29, that would be what would happen, and it'd be an incorrect calculation. Okay, so we got to do 0.29 divided, I'm sorry, I'm not doing it over here, by 2 equals, it's 0.145. So now let's try this calculation again with 0.145. I'm not going to rewrite it on there, but I just wanted you to see what would happen if you didn't think about the fact that you got to split this between these 2 tubes, because you're doing cathode bias on a push-pull system. Okay, so now we're going to do the 80. Okay, 80. Oh, I'm sorry, here, I'm not back over again. Times 0.145 equals 11.6. All right, so now that changes that number. Instead of 23.2, it's 11.6. all right, now if you look at the book, and like I say, I'll show you how to look that up later, but for a 6v6, the max plate dissipation that you can have for a 6v6 to not run too hot is 12. 12 watts. This is watts right here, 11.6. That dissipation means it's for watts, okay? All right, so we're right at the top end of the tube. The tube could handle it, but they're going to run constantly hot the whole time. And it's smarter to let it run a little bit less than hot. Like I would knock it down a couple. Well, how you want to do that, if your plate dissipation is too high, then we would need to increase the value of one of these resistors down here, preferably, I think this is the end of the can dome right here, preferably this guy right here. I would increase that. Maybe, I don't know, you'd have to play with it, but maybe put 400 in and then put a 400 ohm in there and redo your calculation. And you need to just knock that down to where it's not 11.6 but maybe 9.6, you know what I mean? That would give you a good strong running, but it would not be too hot for that tube. So each tube is going to run at 11.6 on watts. And so those things are going to run right at the cap end of where you need to be with this configuration. That's if my 80 volts, which is probably wrong. I'm just hypothetical, but if you measure that plate to cathode, it's probably not 80 volts, and so that's probably what's throwing this calculation off. But that's just hypothetical. If that's what you got, then you're going to need to increase the value of this. If your plate to dissipation come out too low, let's say it come out like to 5 something, then you're going to want to decrease the value of that, okay? And you decrease that value, that'll help that dissipation to change to a higher dissipation. You want to just try to be a little bit below the max. I think that would be the best setting that you need. I'm not going to go into, this is the cathode bias, okay? And I will go into the other bias for the fixed bias and the grid bias. I'll go into that one when we run across it in the radio. I'm not going to go into it until we run across it because it's a little more complicated on how to calculate that. It uses the same concepts, but it's a little more complicated, and I don't want to confuse you. I want you to absorb what we just did here. All right, so if you want to, I'm going to hold it right there for a second, get out of the shadows. So let me get a better hold. I'm going to let you maybe take a screenshot of that, and that way you can kind of get your layout. You can draw your little graph to lay that out. I'm not talking about my numbers. Don't use them, but those are just hypothetical numbers. But just the calculations you need to do that. So this is the other side. This is the one side for the output transformer, and then this is the side that's coming into your output tubes, and that'll help you. Now this current calculation you can do anywhere in the radio. If you want to find out where current sum is, you pick your resistor, you measure the resistance across that, and then you measure the voltage drop across it, and then you do your division. You do your voltage drop divided by your resistance. And that'll give you a current wherever you're at in the radio. And there's going to be a lot of times you're going to need to know if you got high current somewhere. And you'll know that when you look at your meter up here, when you plug that thing in and you get real high current, then you can start testing different places and see where your current's high at. And you can use this calculation. This is your first introduction to Ohm's law. Now I'm not going to give you the actual the math equation. Like a lot of this, there's math equations. It's I'm not even gonna confuse you with that. But I will introduce you to those later on. We get a little bit stronger. I'm going to introduce you to the actual terms that they call these things. I'm using redneck terms, and I'm giving you just basic words for this. But there's actually, they have like VR, and they have for current, I think it's high. But what I'm saying is there's so many terms, and they've run into mathematical equations on Ohm's law, and that's fine. I will show you that it's coming, but I just want you to be a little more relaxed up front here so you can learn the formula before you learn what all it's called in real life. I'm just giving you some basic concept of how to do it, and then we'll learn the proper terms and the actual mathematical equation that goes into this, because there is a little mathematical equation that you plug this into. I just broke it down and simplified it so it makes it easier for you to do it. Now this is to do your cathode bias tubes, if you have cathode bias. So like I say, how you tell that, and I showed that on that first segment, is you tell that by if your cathode is not directly grounded, like this one is, where the cathode goes straight to ground, but it goes through a resistor to ground. More than likely you're at a cathode bias situation on these output tubes. And then you know how to calculate your cathode bias to find out what kind of plate, how many watts you're shoving at that thing by your biasing, depending on how big that resistor is. If you got the wrong size resistor in there, you're making these things run too hot or too cold, you'll know when you do this calculation. So that kind of helps you calculate this side. Now you know how to calculate this side. And yes, this is not in all cases. There's rare things that it varies a lot, and we're just talking about on a lot of the cases, this will help you calculate that. And then single-ended is the only thing difference is on the single-ended cathode bias is you would use that original number we had, not divided by 2. All right, and you understand why we divide it by 2, because you got two tubes sharing that current, and so you have to split that current between the two. All right, I hope that answers any questions. I hope you enjoyed this Timeout Tuesday. Every Timeout Tuesday, I'm gonna give you a little bit of a tidbit. I will tell you this just shortly, maybe tonight or tomorrow. My video where I went down and acquired my Philco, and it was a Model 70. It's gonna be coming up either tonight or tomorrow. No, I'm sorry. When I say tonight, I take that back, because this is not coming out till Tuesday, so it'll be coming out before this. That video will be up before this video comes out, so forget I just said that. I thank you for watching, but we went down there to pick up that radio. All right, I appreciate you watching, and shoot me with any questions you might have. I thank you for everything you guys have done, and I appreciate getting these comments like this, because it makes me think, and it makes me go study a little bit before I talk. So you get this stuff in your head, but then, if you don't use it every day, you tend to forget it sometimes. And hang in there with me. It's going to be fun. Well, welcome back. I hope you enjoyed what you saw today. I hope everything was educational and helping you to grow a little bit. Yeah, I still bumble around. Sometimes I get nervous when I'm in front of the camera and I say things. One of the things I said on that correction video on the last one is I pointed at the first IF transformer, and I pointed at the primary of the first IF transformer, and I called that the first IF, and then when I pointed at the secondary of the first IF transformer, I said that was the second IF. And I know that confused probably some people, but the both sides, you have a primary and a secondary of the first IF, and you have a primary and secondary of the second IF. I know that. I just said the wrong thing. I was pointing at that, and I should have said the primary and the secondary when I was talking about those different dimensions on there. So I mess up sometimes when I get a little nervous on there, or I just say things and I don't know what I'm saying that's coming out of my mouth. My brain says one thing, my mouth says another. So I appreciate your patience with me. Nobody pointed that out. I just happened to be reviewing the video and I saw that and I thought, John, what are you doing? And this is on a correction video, so now I'm making a correction to a correction video. Just kidding. I hope you please come back. I'm going to have a lot of content coming at you, and it is going to get better. I keep correcting these little things I'm doing, but I'm trying to find ways to put a permanent correction on some of them. So hang in there with me, and thank you for watching today.